Okay, good morning everyone. Thanks for getting up bright and early. Hopefully you'll be rewarded. We've got three excellent speakers in this Methods and Theory showcase. So our first speaker this morning is David Firth from University of Warwick.
Thank you. Thank you everybody for coming in at 9 o'clock in the morning. So I see myself really as the warm-up act for the serious stuff that comes later. I'm going to talk about something that mixes two of my interests, statistics and football. And actually, I realize I have a rule about this kind of work that mixes those two things, which is that I only do it at evenings and weekends. And so I'm breaking that rule here by talking about it on a weekday. And I just realized it made it seem like I've got more than two interests, which actually is probably not quite true. What do I mean by a spade ranking? So I mean a ranking table that looks something like this. So this is actually a prediction of the end of this season's Premier League in terms of the position of each team. And this is a prediction published by a small company in London called Decision Technology. And there are lots of predictions like this around on the web at the moment. The form of the prediction is that for every team it gives a probability for their finishing position. So Decision Technology is currently saying that Manchester City has an 89% chance of winning the league this season, 10% chance of coming second, a 1% chance of coming third, and essentially zero. I mean, these aren't real zeros along here, but they're too small to write down. And the same for every team. And we can read it across, as I just did, or we can read it down. So, for example, in first place, we've got 89% chance for Man City, 10% chance for Liverpool, and 1% chance for Chelsea, for example. So that's it's a predictive distribution, but an incomplete predictive distribution. It doesn't give us a probability for every possible ordering, for example, of the teams on this left-hand side. So if we wanted to know what is the probability that the teams finish in exactly this order, we can't get that from this table. All that we get is this sort of marginal view of the probabilities in each row or in each column. And that's what I'm calling a spade ranking. So it's not quite a predictive distribution in the usual statistical sense. And so I needed a new word for it. And I'm using this old Scottish word, spé, which means predict, and spade is the past tense of predict. So it's a predicted ranking in a Scottish sense. And I'm using the word spade then in a technical way to denote a table which is an incomplete prediction of exactly this kind. As I said, these things are in a lot of places, and possibly even more famous is 538, Nate Silver's website in the USA, who do this routinely. After every match, they update their prediction of the Premier League, and the corresponding probabilities for winning the Premier League are over here in this last column. So they're giving 63% chances to Manchester City for winning the league at present. This is an incomplete spade ranking because they don't say what Manchester City's probability is of finishing second or third. They just talk about qualifying for the UEFA Champions League or being relegated. Those are the only three categories that they distinguish. So in that sense, it's incomplete or partial. Well, the focus of my talk is not about producing these tables. I have to say, I don't really do prediction of football. It's anathema to me. I like football because of its unpredictability. But when I saw this table, first of all, I was struck by its beauty, and then I started to think about the numbers in it and whether they actually make sense to me. And actually, 89% chance for Manchester City at this point in the season, this is after 3 matches, this was last week, makes no sense to me at all. And so then I started to think, well, how good or how bad is this table, and how can we assess it? Well, we can only assess it by looking at what happened at the end of the season, and we can't know that until we get to the end of the season. So actually, the table I'm going to look at to illustrate the talk will be one from last season. So corresponding one from last season. So just to digress for a moment and say why I'm calling it a spade distribution and not, for example, a predicted distribution or an expected distribution or an expectation. It's because all of these other terms have some ambiguity about them. In statistics, when we talk about a predictive distribution, we mean a probability for every possible outcome, and that's not what we get from a spade ranking. In a sense, that table is an expectation of a predictive distribution, and indeed that's how these companies that publish them get them. They have a black box prediction engine, which is based on a model for the outcome of every football match for the rest of the season, and then they aggregate over that. So they're taking an expectation. So it is an expectation, and we could call it an expectation, but the phrase expected rank has a different connotation, I think. So if we talked about, for example, the expected rank of Manchester City on the basis of the table I just showed you, you'd say that's somewhere between 1 and 2. And that's not what the Spade ranking gives. That gives us quite a bit more than that, because it gives us the uncertainty around that as well. So Spade ranking is exactly what I gave that. It is an expectation. It's an expectation of a table of zeros and ones, which we won't see until the end of the season. So at the end of the season, we will see which team gets rank J for every J. And if we think then about constructing the binary table, which indicates the position of every team, and I'll show you one of these in a moment, then that's the thing that we might call the outcome YTJ, and that's what the Spade ranking is intended to be the expectation of. Another phrase for this is that it's the marginals matrix, because every row is a marginal distribution and every column is a marginal distribution from that full predictive distribution that we don't see. Okay, so how do we assess a prediction like that? Well, we need to have the end of season outcome in order to make such an assessment. And so I'm going to look at last season. And in fact, I'm going to look at a table from February 2019, which is the very first one of these that I saw and was struck by its beauty. This is also published by Decision Technology in London. And at the time they published it, this was the standing in the Premier League table. Manchester City and Liverpool were tied on 65 points each, with Liverpool having played 26 matches and Manchester City having played 27 matches. So on the strength of that, just as a football fan without a sophisticated model, I would have said that Liverpool probably had the edge. And in fact, if you look forward to the end of the season through their fixtures, Liverpool probably had the, on paper, easier run-in of the two teams. But anyway, here's the prediction that Decision Technology put out on the 23rd of February 2019. So this is with 12 matches still to play for most teams in the Premier League. They were saying 58% chance that Manchester City would win the league and a 40% chance of coming second, or 58-42 between Manchester City and Liverpool for winning the league. And that struck me as a bit odd on the basis of what I'd just seen in the league table. So I actually had a bit of correspondence with Decision Technology about this, and they said, oh, well, we have a very sophisticated model, and this is what comes out of it. And so that's really what led me to think, well, how, at the end of the season, am I going to assess whether my intuition about this was good or not, and whether this is actually a good prediction or not? So what the essence of the talk will be how to compare this table with the outcome at the end. And the outcome at the end will be a matrix of the same size, full of zeros and ones, with a 1 in each row and a 1 in each column, indicating who finished in each position. And there is that table from the end of the season. So what I've done here is to light up in orange the finishing position of each team. So Manchester City actually did win the league, of course, last season. I say of course, some of you will know of course, and others not. But they didn't get everything right, but of course they shouldn't in some sense. Statistically, there ought to be they were expressing uncertainty here, and what we're seeing here is evidence of that uncertainty in the finishing positions relative to, for example, the diagonal of this table. Some are on it, some are off it, and that's what you'd expect to see from a good prediction, actually. If they're all on the diagonal, you wouldn't really call that a good probabilistic prediction, because the predictor would have put in more uncertainty than they actually had. So what I'm going to talk about is a method for comparing the numbers in that table with the finishing positions highlighted in orange there in that table. So how to do that? Well, there are standard methods for scoring probabilistic predictions, predictive distributions, and these are very well known, nothing new here. The idea of a proper scoring rule is to construct something which penalizes a bad prediction by comparing the observed with the expected, that is to say the binary observation each binary observation with its probability, and then penalizing it in some way. And there are two standard penalty functions that I'm going to mention here. There are many more in the literature. Both of these are what are called proper scoring rules. The first one is the so-called Breyer score, which just takes squared deviations between the 0, 1 outcomes and the probabilities. And the second one is a more severe score in some sense, the logarithmic score. And I say more severe because whenever pi is 0, this kills the prediction. This really penalizes it infinitely. You get minus infinity, and so you get an infinite penalty for a prediction that says there's probability 0, and then the event actually happens. Now, I didn't want to use this second one because, of course, those zeros were not true zeros in that table. They were just very small numbers that were too small to report. So it seemed unfair, in some sense, to use this very severe penalty. So the one I'm going to use throughout the rest of the talk is the Breyer score, although everything I say will apply more generally to any proper scoring rule. A proper scoring rule, these are scoring rules, a proper scoring rule is one such that the expected score is minimized by giving true probabilities. That is to say, a faithful reflection of your real uncertainty about the outcome. Okay, so that's what I'm going to use. How do we do it for a spade ranking where we don't have the full predictive distribution? That general formula was for a full predictive distribution. Well, we can apply it to every row separately, or we can apply it to every column separately, and it turns out we get something very similar if we do it either way. And it remains a proper scoring rule applied row-wise or column-wise, and that's a nice feature. Okay, so there's the table we started out with. There's the table with the finishing positions lit up in orange. And what I'm going to do now is to apply the Breyer score down columns here. So I'm going to look at this as a distribution of across the teams who might finish first, across the teams who might finish second. I'm going to look down each column and score each column according to how well the prediction did. And the numbers in orange here then are the values of the Breyer score. I've multiplied them all by 100 to make them easy to look at, but they're the values of the Breyer score. 35 is the Breyer score for the first position in the league. Now, 35 on its own doesn't tell us anything. In order to assess 35, we need to know, well, what's a reasonable expectation for that Breyer score in the first column? Well, you can calculate the expectation just from the probabilities. We don't even need the outcome, of course, to get the expectation. And the expectation, I'm giving the expectations here in the gray numbers at the bottom. The expectation in that first column was 49. So in that first column, the outcome that Manchester City came first gets a Breyer score which is smaller, or if you like, better than the expectation. So they did better than expected for the first place, better than expected for the second place, worse than expected for the third place, and so on. Now, what we should like to see, I think, across the bottom here, is that roughly half the time a prediction does worse than expected, and roughly half the time better than expected. And that is roughly what we see here. In fact, I think I counted 12 times this particular prediction did worse than expected, and the rest better than expected. So no particular evidence there of a bad prediction, which is reassuring, I think, for the decision technology company. Now, for the rest of the talk, the remaining 2 minutes or so I'm going to speak, I'm going to just look briefly at what to do to get a single number assessment of this. So suppose we just add these numbers up here and look at the total expectation. Well, the total is 1,476, and the expectation total is 1,394. So in total, we get something that's bigger than the expectation. We could do the same thing by rows of the table, and it turns out we get exactly the same numbers, as we have to, algebraically. Well, I say exactly, there's rounding error involved in these numbers in the table, so actually it's 1 out in both cases. But mathematically, they're the same numbers. So how do we assess this apparent excess, 1476 over 1394? It looks like maybe they did a bit worse than expected, but is it a lot worse? Should we take it seriously or not? Should they take it seriously or not? So what I'm going to look at is how bad was that spade ranking relative to what could reasonably be expected. There are other questions one might ask about comparing competing SPADE rankings, but I'm not going to look at that today. So what I'm going to try and just motivate in the last minute or so is definition of what I'll call a Q-value, because p-values are out of fashion, so I'll call this a Q-value, but it's the same thing really as a p-value, which is to look at the probability under the SPADE ranking. What's the probability of getting a value that's at least as big as the one we did get, or indeed at least as small as the one we did get if we saw an unrealistically small one? The technical problem to solve here is that the SPADE ranking is not a complete predictive distribution, so we can't actually calculate these probabilities directly from it. We need a distribution for that. And so what distribution should we use? Well, I argue that a natural choice is the most diffuse distribution that's compatible with the SPADE ranking, and that's the maximum entropy distribution, and its form is well known. I discovered, while reading about this, a very beautiful paper by Verducci from a long time ago, 1989, whose title doesn't give away any connection with this at all. It's called Minimum Majorization Decomposition, but it's a beautiful piece of algebraic work that relates to exactly this problem, the maximum entropy distribution. Well, the maximum entropy distribution is in this exponential family. And in fact, it's where this exponential family crosses the set of all distributions that agree with the SPADE ranking. So it's a beautiful thing. It's an exponential family. There's almost nothing in statistics that's more beautiful than an exponential family. Verducci's paper is mostly about this is a very high-dimensional exponential family. It's a distribution over 20 factorial rankings for the Premier League, for example. It's huge. And Verducci's paper was all about how to use some clever algebraic tricks to get some idea of the value of theta that matches the observed SPADE ranking. It turns out we don't need all that. And I connected it with another piece of work, which seemed unrelated as well, which is a JRSS paper, which gave the idea of how to do this using a very simple Metropolis Hastings scheme. So actually, Verducci's work, although it's beautiful, turns out to be not specifically useful for this. And the real clues are in this table, which show how to do it via a Metropolis Hastings method. So that's what I've implemented. I'm not going to show you results from that because they agree with what I showed you before. There's no evidence really that that particular prediction that I showed you is a bad one. So what's coming? Well, I need a couple more weekends, and then I can finish the paper and the R package that do all this. And then later, hopefully that will be taken up by the people who produce these things or by other people to assess people's SPADE predictions, SPADE rankings, to improve their methods, or maybe to give prizes to the people who perform best. And maybe, so I know SPADE as a Scrabble word only, and maybe this will somehow popularize it beyond that, in my dreams, perhaps. Anyway, that's the idea. Thank you for listening.
Okay, so our next speaker is Heather Batty from Imperial College London.
Okay, thank you very much for coming. I'm going to talk about regression broadly defined. So for each study individual, we have data on a response variable. So this might be a continuous response. So we have data on a response variable. Could be a continuous response, binary response, potentially censored response, like survival time, or whatever. Okay, and we also have data on a vector of potential explanatory variables. And I'll be speaking about the situation in which the number of potential explanatory variables far exceeds the number of units or the number of study individuals. And this setting arises particularly in genomics, where the number of individuals is typically 50 to 100 or so, whereas the number of variables might run into the tens of thousands. Now, in the context of this genomics example, the goal is usually understanding, so scientific understanding of the data generating mechanism. It's not usually prediction, and the distinction is quite important. So for prediction, there may be several models that are more or less equally effective, and any choice between them is then rather arbitrary. Whereas if understanding is the goal, it's not enough to pick one arbitrarily. Okay, and model in this setting has a very particular form. I'll come back to that in a moment. Now, it's critical in these situations where there's more things to estimate than there are independent observations on such things, to assume sparsity in some sense. And in the present context, there's a very natural notion of sparsity, and that is that relatively few of these very many potential explanatory variables have a real effect. And of course, we don't know which ones. So sparsity is just part of the model, and it plays the role of any model, which is to provide a succinct approximation to the data generating process, critical for interpretability and statistical stability. Okay, so a very powerful method of analysis in this high-dimensional regression context is the lasso. So this penalizes a suitable loss function for departures from a sparse solution, delivering a sparse solution with adequate fit. So the loss function depends on the context. It could be a least squares loss function if we're doing linear regression, or more generally a negative log likelihood. So the penalty term effectively forces many of the regression coefficients to 0. But there results a single model, whereas there may be more than one model, or there may even be many models that are more or less equally effective or equally compatible with the data. So what I'll speak about is a different approach whose aim is essentially a confidence set of models, so a confidence set of effective, simple representations. And this is joint work with David Cox at the University of Oxford. So I'll explain the procedure, and then I'll just give some informal motivation for why this is appropriate. I won't have time to go into the more theoretical justification for this. Okay, so let's suppose for simplicity that we have 1,000 potential explanatory variables. So arrange the indices of these variables at random in a 10 by 10 by 10 cube, and then we're going to consider sets of variables 10 at a time by traversing the cube, so going across the cube by rows, down the cube by columns, and through the cube. So each variable has associated with it 3 sets of 9 companion variables from each time the traversal of the cube passes through that variable. So for instance, this variable has associated with it this set of 10, or this set of 9 companions, this set of 9, and this set of 9. Okay, so then we would just fit a standard low-dimensional regression of suitable form to each set. And on the basis of these 3 analyses, we'll either retain or discard variables according to some decision rules. So we may, for instance, retain variables only if they're among the 2 most significant in at least 2 of the 3 analyses in which they appear. Or we may retain all variables that are significant at some arbitrary threshold in at least 2 of the 3 analyses in which they appear. Now, the procedure will probably need to be repeated. So if say, 100 variables are retained, you would arrange the indices of those variables at random in a square, 10 by 10 square, and repeat the procedure. And the goal is to be left with a manageable number of variables on which we can do informal checks. So this is the kind of exploratory data analysis that's standard in much statistical work. So perhaps 15 to 20 or so. So we'd be looking for interaction terms, nonlinearities, and so on. And then the final stage of the procedure is to test all low-dimensional subsets of this comprehensive model for compatibility with the data. So the comprehensive model is all variables retained through the reduction phase and any squared or interaction terms, etc., suggested at the exploratory phase. Okay, so it would be a likelihood ratio test of low-dimensional models against this comprehensive model. And any low-dimensional model that passes this test comprises our confidence set of models. So I've put confidence set in inverted commas. It can be made to have the kind of formal statistical properties associated with confidence sets, but I won't have time to go into that. Okay, so there are 3 phases. A reduction phase uses significance tests as an informal guide to discarding variables. On the reduced set, an exploratory phase allows the assessment of anomalies. And finally, we assess all these candidate models, low-dimensional candidate models for their compatibility with the data. And typical output would look like this. So it's a list of models. The total number of variables, or total number of columns here, is the number of variables in the comprehensive model, so all variables retained through the reduction phase and any squared or interaction terms. I've recoded the variable indices so that they fit on the page. But if I remember correctly, variable 19 was an interaction term between one of these two. Okay, and this arose from an example with approximately 130 individuals, of whom 105 had osteoarthritis, and the remaining were controls. Okay, so this is what I'm about to say is the key message in this talk, and that is that statistics can take us no further. So statistics is unable to distinguish between models in this confidence set, and therefore it's misleading to report a single one. And really, we ought to be reporting all of these. So any choice between such models would require either subject matter expertise or additional data, so perhaps from a designed experiment specifically designed to narrow down these conclusions, if that was feasible. Okay, so one could construct summaries in an attempt to extract compact messages from these things. So for instance, the proportion of models in the set of well-fitting models, or the confidence set, not containing variable B, that do contain variable A. So this is sort of telling us which variables are substitutes for one another. So if variable B is not included, what comes in to take its place? But I think we have to be careful not to overinterpret things, and really the whole set of models ought to be reported. Okay, some very informal motivation. So our response variable was Y, and our covariates were denoted by X. So our data are realizations of Z. Now, let's just ignore any practical issues arising from the large dimensionality for a moment. In that case, it would be reasonable to do the following. So for every low-dimensional model, we can consider the non-zero parameter vector theta m, and we can identify the corresponding sufficient statistic Sm for theta m. And then we can consider the conditional distribution of Z, conditional on this realization of the sufficient statistic. And if the data we observe is not extreme relative to this conditional distribution, then that model is compatible with the data and should be reported in our confidence set of models. Okay, so sufficiency represents a separation of the information in the data into that relevant for estimating the parameter of a given model and that relevant for assessing the adequacy of that model. And these are traditional Fisherian ideas. I wasn't able to find the exact reference, but it's a paper towards the end of Fisher's life, which highlights this, and it's also discussed in Arndorf Nielsen and Cox's book. So really the only issue here is that because we're in such high dimensions, considering all these low-dimensional models in turn is too computationally challenging. And this is why we have this reduction phase. Okay, so further comments on the reduction phase. When I described the procedure, I said we had well, suppose we had 1,000 potential explanatory variables, so that's a perfect cube. But there's no restrictions to perfect cubes or perfect hypercubes. So it doesn't matter if some of the entries of the cube are empty. Now, if you have very many more than 1,000 potential explanatory variables, it would be sensible to arrange them perhaps in a higher dimensional hypercube. A historical remark is that the arrangement of variables in the cube is that of partially balanced incomplete block designs proposed by Yates 80 years ago. The procedure effectuates a more severe reduction than marginal screening because it requires more of a variable than that it has explanatory power on its own. It also requires that this explanatory power isn't explained away by other variables among these companion sets. And of course, there's some randomness in which variables appear together. But it gives you a very strong reassurance over the security of the conclusions if upon re-randomization of the variable indices in the cube, you get more or less the same answer. And this is actually a very useful way of tuning the procedure. So there were a number of decision rules involved. But if you seek stability under randomization or re-randomization, this is an effective way of tuning those decision rules. Prior assessment of importance can be accommodated. So if there's an intrinsic variable such as gender, which is known to have an effect, this could be included in all the regressions that are run. Or some variables could be included in the cube more often than others, although that would require some thought that we haven't gone into. The procedure is a version of backwards elimination. So this means we start with everything and we gradually discard variables, as opposed to forward selection, which would start with nothing and gradually pull them in. So the lasso, or at least algorithms that implement the lasso, are a version of forward selection. And in simpler contexts, both would be likely to be effective, but we think for what we're trying to do, which is to construct confidence sets of models, backwards elimination is more appropriate here. Okay, so I'm not going to say anything about the formal statistical properties. There's just a reference. Our goal here was really to provide guidance on the decision rules rather than to set up a procedure to achieve pre-assigned error rates, but that's something that's worthy of consideration as well. So I think I'm actually just going to skip all of this and go to the end. So the key point was that it's misleading to report a single model if statistics is unable to distinguish between many, and this view is in contraposition to that implicit in the use of the lasso and related single optimization or penalization-based methods. So we've outlined a different approach whose aim is essentially a confidence set of models. And any choice between them would be based on subject matter expertise. Okay, so thank you.
Okay, thanks very much, Heather. We have time for a couple of questions, if anyone has any. Yes.
It's really just to make Rob run. That was really, really interesting. Thank you very much. I wondered, in a practical sense, there's obviously been quite a lot of discussion, particularly in climate modelling, about producing model averaging and presenting not confidence sets of models, but actually saying there are lots of competing models, and how do we make the best use of all of them in producing our predictions and reflecting on the uncertainty in some of those predictions going forward. And I wondered if you wanted, or if you could, say a little bit about how you see what you've been developing might fit into that type of landscape.
Yes, well, I suppose, although I said that prediction was quite a different thing, we are always interested in causal predictions, in the sense that they're more likely to be stable and under different data than the ones we observe. And so, yes, if you have a confidence set of models, you could also have a confidence set of predictions with their associated uncertainties. So it would be a different way of doing that kind of thing.
Yeah. You were first to raise your hand, so let's go.
Thanks. Hi, that was really interesting, and I can see quite a lot of use for it. I'm concerned that I might be misunderstanding your model selection phase, though. So I wondered if you could just flesh out how the models are chosen, and do you ultimately present all aspects of that cube that were fitted, or do you select the models that you think fit a given criteria to go into your final set?
So the purpose of the cube is just to reduce the number of variables to a manageable number. And once you've done that, then it's really classical statistics. So you have a comprehensive model, you assess by a likelihood ratio test, or perhaps a more specialized test, whether these low-dimensional subsets are compatible with the data. So do they fit as well as the comprehensive model? And if they do, they go in the confidence set.
Could I just further ask then, is it affected by, I guess, your multiple comparisons kind of element?
Okay, so perhaps something that needs to be said is that because the comprehensive model is selected in the light of the data, it fits better than an arbitrary model embedding the one to be tested. And therefore, a likelihood ratio test would reject the null hypothesis that it fits as well as the comprehensive model too often. I think I've got that the right way around, in hypothetical repeated use. And so the way around that is, or the simplest way around that is to split the sample. So that's, I think your comment is relevant to that point.
Okay, so it looks like there'll be a few people trying to catch you in the coffee break, but I'm afraid we have to move on. Sure. So let's thank Heather again. So our next speaker is Andrew Yu from the MRC Biostatistics Unit in Cambridge.
Okay, good morning, everyone. So I'm going to talk us some joint work with Rob Gowdy and Brian Tom. We're all from the MRC BSU. And we're interested in quite a general class of problems. I guess some people might call this dealing with selection bias. We're interested in when the data set we have isn't quite representative of the population or the distribution we're interested in. So we believe there's some kind of additional sampling mechanism which the data goes through before it gets to us. So I guess traditionally we might associate this with survey inference. In that case, we believe the sampling mechanism is in principle chosen by somebody, so it is known. But we're also interested in observational settings where the sampling mechanism isn't known. So for example, something like missing data, you can view the missingness mechanism as a form of selection. And I suppose certain problems in causal inference you can also view as a missing data problem. For example, if you wanted to estimate an average treatment effect, you could view that as two arms of a missing data problem. You could view the treated and the control separately, and so you'd be effectively doing this twice. So in practice, it's quite common to do this using a kind of estimating equation or kind of semi-parametric approach. In that case, you would probably end up involving inverse probability weighting in some form. And the advantage of this is that there's a lot of standard software out there now, and it's probably quite simple to implement these estimators. And also there's a lot of very kind of clever, elegant theory behind kind of asymptotic properties of these estimators, and you have kind of nice properties of estimators like double robustness, which you may have come across, and I'll come back to that later. But the downside to this is you might actually have to rely on this asymptotic theory a bit too much. And if you just have one data set and you're not quite sure if you're in the large sample regime or to what extent you're in that large sample regime, you might not be feeling too confident about just applying some asymptotic theory to that. So if that's the case, then you might want an alternative approach. In that case, you could take a Bayesian approach, perhaps, because you could use a prior distribution as a form of regularization to trade off bias and variance. And if you have it, you can also incorporate some informative knowledge about your parameter of interest, too. The downside to that is that you probably need to have stronger modeling assumptions, and some might see that as a kind of loss of robustness. You're less flexible than the kind of estimating equation approach. So we think we have another alternative which, to an extent, offers the best of both worlds. So by that, I mean is an approach that kind of offers calibration to the kind of frequentist approach, but it also allows you to do kind of Bayes-like inference. So you can specify your prior just on your parameter of interest, and you can have kind of approximate posterior inference. So to do that, we use an idea called the Bayesian exponentially tilted empirical likelihood, which I'll refer to as BETL for short. This is a more general approach which tackles moment condition models. And the reason it's relevant to our problem is because these estimators are generally based on estimating equations. We can actually use those to define a set of moment conditions and use that to define this kind of likelihood function, and then use that for Bayes inference. And we show that actually if you use this kind of posterior, as you get more and more data, it actually becomes calibrated to what you would get if you used the estimating equation approach. So in a sense, it allows you to be somewhat kind of agnostic about how far into the kind of large sample regime you really are. And if you're not kind of far enough, you do have your prior to kind of lean back on. Okay, so just to kind of introduce this idea, I'll just kind of take a step back and look at a more kind of general setup. So suppose we just have a parameter theta naught that we want to perform inference on, and it's associated with a distribution p naught, and it satisfies a moment equation given by a function g. So if you allow this parameter theta to vary across values of a parameter space, then this actually defines a seven-parametric model, because you can just restrict your distributions which satisfy this equation for some value of the parameter. So the very simple examples are things like mean estimation and linear regression. You can view that in this perspective. So if you have IID data from this distribution, I guess a standard approach is you could take a kind of empirical estimate of your moment and then solve for zero, and intuitively it should be kind of close to the true value, as long as you get enough data at least. So this is M estimation, or some might call it Z estimation. And indeed, under some regularity conditions, this estimator will be root n consistent, and it'll be asymptotically normal, kind of the usual nice stuff. And you can maybe estimate this covariance matrix using the bootstrap or a sandwich estimator or something like that. Okay, so that's the general setup. We can also use this function g to define something that looks like a likelihood. So I'll try and break down what's going on. So this is the exponentially tilted empirical likelihood, and it's defined up to a constant of proportionality as a product of probabilities adding up to 1. So we have one probability for each of the data points. So each one corresponds to one of the observed data values. So I guess we could think about this as a kind of multinomial likelihood, because we do have a product of probabilities. So kind of multinomial distributions supported on our observed data values. So you notice that it's a little bit weird because we're kind of defining our likelihood based on the observed data values. It's almost like we're kind of, it's like a kind of oracle thing where we kind of view all our observed data values as being the full support. So this is the reason why it's not quite full likelihood. There's a kind of like kind of going back and defining it after we've seen the data. So for each value of theta, we choose the multinomial distribution which solves this convex optimization problem. Effectively, what we're doing is we're finding the multinomial distribution which is closest to the data while satisfying this moment condition for the multinomial distribution. Alternatively, you can think of this as a maximum entropy distribution while satisfying this constraint. So this is almost like a set of Marshall-Nomura distributions parameterized by theta, apart from the fact that we do need to look at the data first before defining it. So it's not quite a likelihood, but actually we show it's almost a likelihood. In fact, it's almost a likelihood that comes from an exponential family parameterized by theta. So I won't go into the details, but you have this kind of exponential tilting thing going on. And what it really means is that it's almost the likelihood from a kind of worst case parametric family. So I call it kind of least favorable. What it means is that I suppose it's, you've taken this big semi-parametric model and you've reduced it to a kind of finite dimensional parametric model in a way that's kind of minimally informative. We want to kind of assume as little as possible in this reduction. Right, so this is almost a likelihood. We'd like to know if we can kind of almost do Bayes inference. So this was suggested in 2005 by Shenak. And you kind of do the natural thing, combine this likelihood function with a prior, and then use that kind of posterior for inference. And her argument was that this posterior could be viewed as a kind of limit of proper posteriors, so it's kind of limiting argument. We take a slightly different approach and think about kind of practical consequences of using this, and we prove a kind of Bernstein-von Mises theorem, which shows that you do get this kind of calibration to the sampling distribution of your M estimator. So remember, we use these moment conditions to define a set of estimating equations and solve it for theta n. Alternatively, we use it for this approach, and actually, you end up getting the same thing. And I think the key consequence here is that your credible regions will be approximately confidence regions as well. And so it has that kind of interpretation, as long as you get enough data. Okay, so I'm going to finally move on to the actual problem we're interested in. So I'll illustrate it with a missing data problem. So very simply, we want to estimate the expectation of an outcome y. But unfortunately, we only observe y for certain individuals where we have this selection variable equal to 1. So we believe there's probably some kind of correlation between selection and this outcome we're interested in, so we can't just take the observed values and average those, because that would probably give us a biased and inconsistent estimate. We do have to make the additional assumptions that we do have additional covariates x, that if we condition on them, we do have this independence of selection and outcome. So we do have this adjustment available, at least we assume that. So I think in missing data circles, this might be referred to as a kind of missing at random assumption. In causal inference, you might view this as x as a kind of a set of confounders, and then you adjust for that. So yeah, we assume the selection mechanism is unknown. I'll just stick to that for illustrative purposes. You could also do this when it's known. It would actually be a little bit simpler. So yeah, again, we're trying to estimate the expectation of y in the kind of population distribution. Okay, so I guess the general approach, if you do this using kind of the semi-parametric theory, is that you specify two auxiliary models. So you have a selection model. So here we regress the selection variable on x. And some call this a propensity score model because of this quantity here, the propensity score. So a simple model would be something like logistic regression. You could I guess, use something kind of more complicated if you want. And you also have an outcome regression model where you regress the outcome on the covariates instead. And this is just a kind of standard regression model. So there's actually a lot of choice when it comes to estimating your parameters alpha and beta. There's a lot of clever work in specifying a set of equations which give you nice properties for your final estimator. I won't go into the details, but if you want to know more, there's an excellent summary in a book chapter by Rudnitsky and Van Stieland. But yeah, effectively, we want at the end of this two estimators for our two models. Okay, and once we have that, we then combine these estimators in a clever way and get our estimate of the expectation. And This form here is motivated by same parametric theory of efficient influence functions, etc. But the take-home message is that it has a nice property. It's doubly robust. What it means is that even if we get one of the models wrong, if we get the other one right, we still get a consistent estimator. So we have this kind of orthogonality of the two working models. It allows us to get kind of two shots at getting the right model. Alternatively, if you use a Bayesian approach, either you use both models, but then you have to get both of them correct. Otherwise, you kind of get one model kind of bleeding into the other, and then everything goes wrong. Or you use the conditional independence assumption, and you ignore the selection entirely. But either way, you don't quite get this double robustness. You don't get kind of two shots at getting it right. So this alternative using the Bettel approach, and what we do is that we take the original parameter we were interested in, and we actually augment it to include all the kind of auxiliary parameters as well. The reason why we do that is now we can view these set of estimators as actually a single estimator which solves a single set of estimating equations. Because how I did it before is I did it in stages. I could estimate alpha and beta first, and then I estimated mu hat later. We actually view it as one procedure. If we do that, we can kind of go back to a set of moment conditions. So first we have the way we estimated alpha, beta, and rho, and then we append it with this here, which is, if I go back to the previous slide, this is how we estimated the final estimator here. If we specify this function here and go back to the estimating equations, it will be exactly how we estimated the estimators previously. So it's kind of trying to mimic how we did it in the estimating equation approach. Right, so we then use this function to construct our likelihood in that kind of multinomial likelihood way, and then use that for kind of Bettel inference. Then the marginal posterior for our parameter of interest will have this calibration. It will be asymptotically normal, and it will concentrate around our doubly robust estimator. So what it means is that we have a kind of analogous Bayesian version of doubly robustness. It will concentrate around the true value as long as one of our models is correct, one of our working models is correct. What's more is that even the credible regions will have approximately correct coverage if one of the models is correct. This is somewhat surprising because actually it's been shown somewhat recently that if you do Bayes inference with misspecified models, you might get posterior consistency, but you almost certainly won't get correct coverage. So the fact that we can actually misspecify part of our model and still get approximately correct coverage is somewhat surprising and quite nice. Okay, so I've gone through a few reasons why you might prefer this to a kind of fully Bayesian approach, but there might also be some reasons you might prefer this to a fully frequentist approach as well. So it might be the case that you have a nice estimator with very, very lovely kind of asymptotic properties, but for finite samples, things might go wrong. There might be some kind of non-zero probability of lying outside the parameter space. So for example, if I go back to this estimator here, if we have, say, binary outcomes, then we'd want our estimators to lie between 0 and 1. But because of this form of the estimator, particularly kind of this pi here, if that gets close to 0, this might blow up and you might actually get something that lies outside 0 and 1. So this offers a very simple way to just adapt your estimator to get something better. Is you can just restrict your prior to be between 0 and 1, in which case you'll just end up kind of averaging over the support you allow it to be in. And so you get a modified estimator, possibly with better finite sample performance. And of course, if you have a distribution to work with, then you can choose from a variety of estimators based on what your problem and what your target loss function is. Okay, so to sum up, we reckon we have an approach which can kind of offer the best of both worlds in a kind of frequentist versus Bayesian way. The way we do it is very simple. All we need to do is take the estimating equation which we use to define our favorite estimator and use that to define a set of moment conditions, use that likelihood function for Bayes inference, and we get this calibration. Okay, thank you for listening.